where f of x equals the Taylor series expansion. In this case, f of x, our independent variable, is temperature. We want to solve for temperature using positional data.
Dr. Rubin?
And so the first step is we find the second iteration, whatever it's called. We do Taylor series until we get to end. So this is our first term, our second term, and our third term. This is our general equation. Then we need to find two equations because we're using 2 points to find 1 point. And so for our first equation, we're going to use our center at x equals I, because that's what we want to find. And our x is at xi plus 1, the next point. And then our second equation we'll do with our center, x equals I, and then our previous point, xi minus 1. So for our first equation, we simply plug in the a's and the x values into this first equation, and we end up with that. Same with b, our second equation, we end up with a similar equation. Then we add them together. So these are the same. Well, these actually they're not the same, but so we get this term when we add them together. These two are the same, so we just get 2 t of I. Remember, f of x is t, so f of x of I is t of I. These equations cancel out because this term is the same, f prime of x of I, or t prime of I. And this, we're going from the future, I plus 1, to the past, or to the present, so that's negative. So that's our negative distance, because the distances are the same between points. This equation, we're going from the past to the present, so it's positive h. And so they cancel out, we just end up with nothing. For the last term, same dealio, we have a negative h and a positive h, and these terms are the same, so we can add them to get, but it's squared, so it doesn't really matter. You square the h's and it doesn't matter. And we can add them together and cancel out that last 2, and we end up with this equation. We can modify it to be a derivative, and then since we don't care about d's, we just turn them into deltas, and we get that.